In this video, we'll talk through the notes for section 2.4, which is called semi-infinite domains. We will look at the heat equation on an interval, which is no longer the entire real line. We'll look at the heat equation on the interval where x goes from 0 to infinity. That's why we're calling it a semi-infinite domain. We'll be looking at the heat equation, which is the same heat equation as before, but now we're restricting our x's to being positive. Notice that we've introduced a boundary at x equals 0. So we need to introduce a boundary term, which we've done here. U at 0, t is equal to 0 for all t, positive t, that is. What this means in terms of the heat equation is that we're assuming that the temperature is constant at 0 along the boundary. And we also have our usual initial condition here. But again, this is for x strictly positive now. We'll solve this problem by turning it into one that we already know how to do. We'll turn it into a Cauchy problem, a pure initial value problem without boundary. So define a new function psi. This function psi is going to be defined as an odd function which is an extension of phi. So what that means is that when x is positive, psi at x is just the same thing as phi at x. But if x is negative, then we want to make sure that psi is an odd function. So for x negative, we define psi at x to be the opposite of phi at the opposite of x. In this way, we get an odd function. Well, we also need to define the function at x equals 0. In order to be an odd function, it's necessary for psi to be 0 when x is equal to 0. We have to add this extra definition in, this extra piece, because phi was not defined for x equals 0. Phi was defined for x strictly greater than 0. So we need to add in this little extra piece here. We now extend our problem to a Cauchy problem. So we have here the heat equation, but now it's the Cauchy problem. So we have the heat equation here, and we have this initial condition, where v at x comma 0 is equal to psi of x for all x. We don't have a boundary condition here because simply we lost our boundary. We no longer have a boundary, so there's no boundary condition. This is a Cauchy problem for the heat equation, and we know how to solve this. We found the solution to this problem in section 2.1. So that means we can write it down, and let's do that. So the solution to this Cauchy problem is written here. V at xt is equal to the integral from minus infinity to infinity of g at x minus y comma t times psi of y dy, where this g is the Green's function, or the fundamental solution, or the heat kernel if you prefer. So we have a solution to this Cauchy problem. Now notice it's written in terms of psi, which is not a surprise since that was our initial condition. However, we can rewrite this in terms of phi, just using some properties of integrals. So let's do that. We'll write it in terms of phi. Now in order to do that, it's necessary to rewrite this integral as an integral over the interval from 0 to infinity, because phi is not defined for negative numbers. So that's what we're going to do. So we're going to rewrite this in terms of phi. So how does this work? We start by, here we've just rewritten the same integral. And what we're going to do is we're going to write it as the sum of two intervals, or two integrals, excuse me. So over two intervals though. So it's an integral from negative infinity to positive infinity. So what we're going to do is write it as an integral from negative infinity to 0 plus another integral from 0 to positive infinity. Now we're doing this because we've defined psi in such a way that it's in terms of phi on these different intervals. So when your interval is positive, the positive interval from 0 to infinity, that is to say that y is positive, we know that psi is just the same thing as phi. So we can just replace it outright. On the other hand, in this first integral, where y is negative, psi of y is equal to the opposite of phi at the opposite of y in order to make this entry positive, in other words, so that phi is defined. So now what we've done is we've already gotten our integral in terms of phi, but we want to combine this into one integral. So we're going to just do a simple substitution. We're going to let u be equal to minus y. So that means that this term right here becomes u. That also means that this dy is the opposite of du. So this thing is minus du. At the moment, we're not going to do anything to this integral on the right. We're just looking at the integral on the left. Notice that we've just replaced psi with phi, however. So let me just, we've just replaced that psi with that phi. Now on the left, we've just done this substitution, or we're doing that substitution. So what are we going to do over here? This minus y is the same as u, so that corresponds to this u right there. This dy corresponds not just to this du, but there's also this minus sign as well. That's also part of it. So these two terms go together. Then we're changing y to minus u, or minus y to u, so we have yet another change, which is this minus y right there becomes that plus u. The other thing that needs to change are the limits of integration. We're swapping u with minus y, so that means it's a reflection. So 0 stays at 0, but so this 0 stays at 0, but now instead of minus infinity, it becomes positive infinity. Again, on the right, we haven't really done anything. We'll make a substitution here just to get everything in terms of u. So we're just going to, on the right, we'll make the substitution y equals u. Then we'll just replace all of the y's with u's and call that one good. Now on the left, we can change things around a little bit. So since we have this minus sign in front of our integral, we can swap the order. So instead of going from infinity to 0, we go from 0 to infinity. In order to do that, we need to use that minus sign. So that's just going to give us an integral from 0 to infinity. But now we have two integrals from 0 to infinity, where the integrand is u in both cases, so we can just simply combine them into one integral. So that's the integral from 0 to infinity of minus, so this minus right here is that minus right there. Well, let me just change the color back to something else, like blue. So this minus sign is that minus sign right there. And then that phi of u is that phi of u, and we haven't really done anything to the g. And on the right, again, we haven't done anything. But we've combined these two. Now you can factor out the phi at u. So we can factor out this phi of u, and that's there. And what that leaves us with is the heat kernel terms. Now notice that we just swapped the order because we have this minus sign here. So it's g at x minus u comma t, that's the first one, minus g at x plus u comma t, that's the second one here. So this one goes here, and this one goes here, like so. So what we've done is we've written v at xt, which is the solution to our Cauchy problem, in terms of an integral over the positive real numbers in terms of phi instead of c, or phi instead of psi. So the solution to the extended problem is right here, v at x comma t. It's the integral from 0 to infinity of capital G at x minus u comma t minus capital G at x plus u comma t, phi u du. And this is valid for all x and r with t greater than 0. To get a solution to our original problem, we just simply restrict v to the set where x is greater than 0 and call that u. So this u is just simply the restriction of v. Now we actually want to include the boundary, so that's why we have x greater than or equal to 0 here. So now we have a solution to our initial value problem, but we do need to check and make sure that it actually is a solution to the boundary problem as well. That is to say, we want to make sure that it satisfies the boundary condition that we've imposed. Remember that we just imposed on the boundary that the temperature was a constant 0. So you need to just check that u at 0 comma t is equal to 0 for all t. And that's easy enough to check. You just substitute in x equals 0, and everywhere that there's an x, that just becomes 0. So there's nothing here. There's nothing here. So you just end up with the integral from 0 to infinity of g at minus u comma t minus g at u comma t times phi of u du. Now, it might not be immediately obvious, but this term is in fact 0. That's because g is an even function. It's symmetric about the y-axis. You can see that here. The only occurrence of x is right here, where it's x squared. So g is symmetric about the y-axis. So that means g at minus u comma t is equal to g at positive u comma t. So these two terms are the same. So in other words, when you take their difference, it's 0. So that means that the integral is 0. And this is true for every t. So what we've shown is that u satisfies the pure Cauchy problem, and if we or v does, and then if we restrict that to get our function u, then it still satisfies the same differential equation, it still satisfies the same initial condition, and we've also shown that it satisfies the boundary condition. So that gives us our solution. Finally, we close this section by remarking that a similar method works when solving the wave equation in a semi-infinite domain, although the process for the wave equation is somewhat more technical.